Hello everyone, welcome to part 17 of my video series on probability distributions. So today we are going to talk about an interesting distribution. Now if you want to understand this distribution, you should learn about chi-square distribution and normal distribution first. So those videos can be found in part 16 and part 3 of this video series. So feel free to check those out first before coming here. So let's dive in. The first thing is this distribution is actually used to compare the variance between two groups. Now the question is, what is variance? So this is the formula for variance. Now with an example, I'm going to illustrate how this formula is actually used to calculate variance as a square. Suppose we have 5 male heights in centimeters and they are 100, 150, 175, 120 and 200. Our first task will be to calculate x bar, which is nothing but the mean of these values. The next task will be to get this summation. So what does this summation represent? This summation represents the deviation from the mean of the data points. So we have 5 xi's right here. So we can make this table and sum everything up, which is 6520. So this is going to be our answer, which is going to be 1630. So this is the variance of these 5 different values. Now, if we had these heights, the variance would be 13. Understand that when we have a lot of spread, so you can see that the heights are very different, then there will be a high variance. But when the heights are going to be quite consistent, then the variance will be low. That means variance is nothing but a measure of how spread out your sample points are. Now, let's look at an example. Suppose you have designed a drug that influences heights in teen boys. So in group 1, we have teen boys who never took this drug. In group 2, we have teen boys who took this drug for over a month. Now, we want to see the variance ratio between these two groups. We want to see if there is a difference in variance between group 1 and group 2. Now, obviously, if you could measure the heights of all teen boys from these two groups, then you could have simply got the true population variance, sigma 1 square and sigma 2 square. But that's definitely not possible because maybe teen boys who never took this drug consists of billions of people on this earth. And people who took this drug also consist of thousands of people. So in order to do this variance analysis, in order to compare the variance between these two groups, we need to sample, right? We need to randomly sample people from these two groups. So we need to randomly take some boys who never took this drug, and we need to randomly pick some boys who took this drug for over a month. So suppose we have 100 samples from group 1 and 100 samples from group 2. So those subset of teen boys, which consists of, say, just assuming 100 from group 1 and 100 from group 2, their variance is not the true variance. So we can call them estimated variance, which is denoted by S1 square and S2 square. Now, when we talk about probability distributions, we talk about the random variable x. So in this case, we just replace x with f. So in f distribution, they just simply use f in most textbooks and other places. So I'm also using that. So f is equal to this formula. Now here, we can assume that there is no difference in the true population variance because we actually don't know the true population variance because we cannot gather all those samples. That is not possible for us. So we assume that these two are equal. So f boils down to this, a ratio of sample variance, right? Sample variance of group 1 and sample variance of group 2. Now we know that S square has this formula. Now if you remember in my chi-square distribution, which is in part 16 of my video series, the chi-square distribution is nothing but the summation of these whole squares, these z squares, right? So if we have n samples, we can think of those n samples coming from n different normal distributions. So we can think of these as z square random variables. Now, the chi-square distribution, which is the summation of n z-square distributions, has a degree of freedom of n. So I think you all remember that, right? So we are assuming that here for this case, this S1 square is actually a chi-square distribution where the degree of freedom is d1, and d1 can be equal to n minus 1 because that is basically the sample number, or you can call it n as well. It's not a big deal. So you can see this is exactly what I've written here. So we have x, which is a chi-square distribution with degrees of freedom of d1 because d1 number of z variables are going to be added here from I equal to 1 to n. And also this denominator right here, it has a degree of freedom of d2 because there will be n2 samples here, n2 sample points here, and that denotes n2 number of z squares being added. And so that has a degree of freedom of d2. So if we simply take this ratio, then we are going to get the f random variable, f random variable from the f distribution. So let me clarify this a little bit further. So you have s1 square and you have s2 square. So in the s1 part in group 1, we may have 100 samples. That means it will be, you can assume that it is a chi-square distribution which has 100 degrees of freedom. So d1 equal to 100. And in s2, in group 2, maybe we have 50 samples. So it is going to be a chi-square distribution of 50 degrees of freedom, 50 df. So that is going to be d2. And obviously, in the variance calculation, we do the scaling. That is why d1 and d2 are below here. So, moral of the story, long story short, is f random variable is nothing but the ratio of two variances, and that can be sort of approximated by two chi-square distributions, the degree of freedom of which depends on the number of sample points we get from group 1 and group 2. If we are getting 100 sample points here, degree of freedom is 100 for the X chi-square distribution. And if we get 50 samples from here, the degree of freedom will be 50 for this Y chi-square distribution. So let's talk about the probability density function. So as I said before, f is the random variable. So you can think of this as x, which we typically denote the random variable as, and d1 and d2 are the degrees of freedom, which depends on the number of sample points we get from each group. So these are the parameters of the distribution, the f distribution. So it's quite hideous. The whole thing looks quite hideous, but let me break this down. So first thing is the f has to be greater than 0 here. F cannot be less than 0 because it's nothing but a ratio of two variances. Number two is this thing. It is called a beta function. So it looks something like this. So you can break this down into this formula. Now the question is, what does this formula represent? So when we say that this is the PDF of F distribution, what does this physically mean? So this is actually very, very important. So if we, I mean, obviously this is a continuous distribution, and we know that in continuous distributions, probability, I mean, you cannot really estimate probability at a certain point. So we cannot say what is the probability of f equal to 3. That is not possible. So if you don't know that, you need to check out the part 1 of my video series. So we can only integrate. We can say what is the probability in the range of 2 to 3. So when f equal to 2 to f equal to 3, what is the probability in this range? So what this actually means is this. Probability of the variance ratio being in the range of 2 to 3 between group 1 and group 2 samples. So hear me out here. So first of all, this F is a variance ratio between group 1 and group 2. So we need to calculate the probability of this variance ratio being in the range of 2 to 3. And we are assuming that group 1 has d1 degrees of freedom and group 2 has d2 degrees of freedom. That means d1 sample points and d2 sample points approximately in these two groups. So this is the last part is also important. We are assuming that their true population variance ratio is 1. That means they have no difference. So in the previous slide, we talked about why we are assuming sigma 1 square equal to sigma 2 square because we have no idea about the true population mean. So simply assume that the ratio is 1. That means they don't have any difference. So if we make that assumption, then what is the probability that this ratio after doing random sampling is in the range of 2 to 3? So obviously that value will not be very big, right? Because if the true variance ratio is only 1, then the random sampled variance ratio shouldn't be that high unless we have a lot of sample points coming up, because the more sample points we have, the more confident we become at our estimate. So what is the expected value? The expected value equation is this, which is very simple, and d2 has to be greater than 2 because the expected value cannot be negative, and if d2 equal to 2, then it will be undefined infinity. So as d2 gets bigger, the expected value becomes close to 1. So understand that if d2 is equal to 3, then this value is 3. But if d2 is 1000, then this is 1000 divided by 998, which is very close to 1. And the bigger d2 gets, the closer we get to 1. Next, variance. The variance equation is extremely hideous. So for the variance to exist, d2 has to be bigger than 4, because d2 minus 4 is right here in the denominator. So the final moral of the story that I want you to take away from here is that among the compared two groups, you should assign the one with higher number of sample points as group 2. So you can see that D2 has a lot of influence on these things. And we are actually very happy if D2 becomes bigger, because then everything is more stable. So always remember that if you have two groups, group 1 and group 2, and you want to compare their variance, and maybe group 2 has a lot of sample points, then assign that group as group 2 basically. So assign the bigger group as group 2. That is the moral of the story from these two formulas. Finally, to look at the probability density functions, so A value will be in the x-axis and density in the y-axis. So we have kept d1 fixed. As we increase d2, the peak the mean sort of becomes closer to 1, and there is lower and lower tail. So the tail becomes thinner and thinner as we increase d2. So when we fix d2 at 20 and we keep increasing d1, there's a shift in the mode. This is mode, by the way. So understand that when we increase or decrease d1, the mean is not changed. The mean remains as it is, only the mode changes. So this is the mode, basically. So that's all about F distribution. If you like the video, feel free to subscribe and share. And you can donate to our channel via the link in the description. Thank you very much.